The entire transition to electric vehicles currently rests on the shoulders of a single technology, the lithium-ion battery. It dominates the market because lithium excels at packing massive amounts of energy into a compact space, giving cars the high performance and long driving ranges consumers demand. But looking at this sprawling network of evaporation ponds reveals the immense scale and complexity required to extract that lithium. Relying on this one element creates heavy exposure to price volatility and supply chain bottlenecks. The demands go deeper. This terraced open-pit mine shows the heavy earth-moving operations needed to harvest metals like nickel and cobalt, which are essential to making modern lithium batteries function. There are also physical limits. A snow-covered electric vehicle plugged into a charging station is a common sight in cold climates because lithium cells lose significant range and charging efficiency in freezing weather. To reach global scale, the industry requires an alternative chemistry, one that prioritizes low cost, extreme abundance, and environmental resilience over maximum driving distance. Every battery cell shares the same basic architecture: an anode, a cathode, a liquid electrolyte, and a separator dividing the two sides. During charging, an external power source forces ions from the cathode across the electrolyte to the anode. At the same time, electrons are stored in the circuit above. When you drive, the process reverses. The ions migrate back, or discharge, releasing the stored electrons to flow out and power the motor. Lithium ions are tiny and light. This allows engineers to pack them tightly together, which is exactly how these cells achieve such high energy density. If you swap lithium for sodium, the physics change. Sodium ions are physically larger and heavier. Far fewer of them fit into the same volume, which caps their energy density between roughly 100 and 175 watt-hours per kilogram. Because of that bulky physical footprint, battery engineers must use entirely different materials for the anode and cathode to house them successfully. These new designs typically use a disordered material called hard carbon for the anode and a crystalline structure known as Prussian white for the cathode. What sodium lacks in energy density, it makes up for in availability. These endless rows of harvested salt represent sodium's greatest strategic advantage. It is one of the most abundant elements on the planet and can be easily pulled from seawater. Utilizing a material this common removes the need to mine expensive, geopolitically concentrated minerals like cobalt. The chemistry is also stable. Viewed through a thermal lens, a highly stressed sodium cell maintains a steady temperature signature. This higher thermal stability reduces the risk of battery fires. Sodium cells also maintain their performance in the cold, retaining roughly 90% capacity even in temperatures as low as -40 degrees Celsius. Sodium provides a combination of cheap materials, rugged winter reliability, and fire safety that lithium cannot match. Lower energy density means sodium battery packs must be heavier for the same amount of power, which makes them less suitable for luxury, long-range vehicles. Additionally, global manufacturing scale for sodium still trails the massive infrastructure currently supporting lithium-ion production. The industry is currently executing a three-step roadmap. Step 1 targets vehicles where durability and cost matter more than range, such as delivery vans, city cars, and municipal commercial fleets. Step 2 involves an aggressive push for scaling. This automated assembly line represents the push for high-volume manufacturing, which is the only way to drive down the cost per kilowatt-hour. Finally, Step 3 establishes a parallel supply chain for components like aluminum current collectors, protecting the technology from shocks in the lithium market. Major battery manufacturers like CATL and BYD have already transitioned sodium batteries from the lab to the street, with commercial deployments and urban vehicle rollouts hitting the market in 2026. The industry is evolving into a multi-chemistry market. Lithium continues to serve the high energy needs of premium travel, while sodium provides the cost-effective, rugged architecture required for affordable mass-market vehicles.